Part C now. Mathematicians were developing a formula to solve cubic equations in the 16th century. The graph of y equals negative 1/3 x cubed plus 9bx plus c for some values b and c passes through the point R. The coordinates of R are 6 and negative 10, and we've got the graph sketched on the right. Find an expression for b in terms of c. Okay, so let's just highlight that. So there's our equation. And we've been told that the coordinates of point R, which if I scroll down, we'll see that's there. The coordinates of that point are 6, negative 10. So x is 6, y is negative 10. So an expression for b in terms of c means we need something like b equals something, 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 c, and then some other stuff. It just has to be b equals, and then there'll be c and other stuff on the other side. And that's what our expression needs to look like. So using those coordinates that we have been told, we can substitute that x and y value into that equation, which will leave b and c as the only letters remaining, which is what we want. So let's do that. So remember, x is 6 and y is negative 10. So every time I see y, which is only the one time, I'm going to put negative 10. Every time I see x, I'm going to put 6. Brackets are always good to use when you are substituting terms in. Need to make sure that we do the powers on the correct thing. I always like to use brackets when substituting. So that's why I have done that, because very important, we only cube the 6, then we times it by negative 1/3, not the other way around. Okay, let's simplify this as much as we can. So 6 cubed is 216. So we'd just like to do one thing at a time, if we can. So I'm not going to times by the negative 1/3 just yet. 216. 9 times 6 is 54. So that's going to be 54b plus c. Okay, well now times 216 by negative 1/3, which is negative 72. So negative 72 plus 54b plus c. So the question wants us to find an expression for b in terms of c. So we need to get b by itself. So take away 54b from both sides. So we'll have negative 10 take away 54b equals negative 72 plus c. So again, our objective is to get b by itself, so we just want to move things away from it until it is by itself. So we'll add 10 next. Always best to move terms that are added or subtracted before doing any division. And we're nearly there. Now, last step, this is to do the division to separate negative 54 from b. So divide both sides by negative 54. That gets b by itself, which is what we wanted, and it doesn't really matter what is on the other side so long as the c is over there, which it is, because all we wanted was to have b by itself. And that is the answer. We've got an expression for b in terms of c, and that is a merit question. To get achieved, doing a correct substitution all the way back at the beginning, substituting those x and y coordinates in is enough for achieved, and then getting all the way to the end, an expression for b in terms of c is a merit. Part 2 of question C is at point Q, it is true that 0 equals negative x squared plus 9b. Using algebra, show that x equals 3b to the power of 0.5 at Q. So here's point Q up here. So we've been told at that point, 0 equals negative x squared plus 9b. So we need to show x equals 3b to the power of 0.5, which is a case of rearranging this equation to solve for x. So we will go, first of all, add x squared to both sides and separate that from the 9b. That's good. We want it on the other side. And now, no, x, not x squared, so we'll square root both sides. So the square root of x squared is x. And we'll have the square root of 9b over here. Square root of 9 is 3, and the square root of b is, well, square root b. We can write that, though, as b to the power of 1/2. So the reason for that is a root. So if you've got a root x to the power of b, you can write that as x to the power of b over a. So we've got b to the power of 1 as a square root. So we've got b to the power of 1 over 2. And remember, 1/2 is 0.5 because we're very close to that. Apart from I've written 1/2, I'll convert it to 0.5 in the next step. Now, we do just need to be careful because whenever you square root something, there's actually two possibilities. So it could be the positive or the negative. So the reason for that is if we think about the 9, if you square root 9, so you might think, well, okay, 3, because 3 squared, 3 times 3 is 9, which it is. But if you do negative 3 squared, so negative 3 times by negative 3, you also get 9. So that is why we have to go plus or minus 3b to the power of 1/2. So mathematically, it could be the positive or the negative. Now, if we go and look at where Q is, so it's up here, so we can see that x has a positive coordinate here because we are on the right-hand side of the y-axis. So if we go down to the x coordinate here, this x value will be positive. So therefore, we're not interested in the negative solution. X must be positive. 3b, I'll just change that power of 1/2 to 0.5. And there we go. So with these questions where you had to do a bit of interpretation, always best to write down that interpretation. So why did we discount the negative solution? We discounted it because we can see that point Q has a positive x value or x coordinate. So x is positive 3b to the power of 0.5. So this is an excellence question. To get achieved, you have correctly solved the equation up to here, or you have left it as a square root, so you could have gone square root of 9b. That's achieved. For merit, you have given the positive and negative solutions, but you haven't discounted the negative solution. to get excellence, you have done the correct working, you've got the correct answer, and you have got this sentence that I've just underlined in yellow. That's what you need for excellence. Is explaining why you've gone for the positive solution and ignored the negative solution. On to the last part of question 1 then. Consider again the curve with the equation y equals -1/3 x cubed plus 9bx plus c. So this is the same one as what we've done in the previous 2 parts. The shape of the curve changes as the values of b and c vary. This in turn causes the lengths of the purple and red lines to vary. Due to the symmetry of a cubic curve, the red lines stay the same as each other. So we can see, if we look at that diagram on the right hand side, the red lines are going from the turning point up to that dotted horizontal black line, which is in line with the y-intercept. And the purple line is going from the y-intercept down to the x-axis. For some combinations of b and c, the curve can intersect the x-axis 3 times, like this one is in this diagram. It's got 3 x-intercepts. If I mark those, they are here, here, and here. So there would be also a combination of values where it could potentially have 1 or 2 x-intercepts as well. A cubic will always have at least 1 x-intercept. But we're interested in specifically combinations of b and c where the curve will intersect the x-axis 3 times. This will happen if each red line is longer than the purple line, which, as you can tell, those red lines are much longer than the purple line. Find the condition that b and c must satisfy for the graph to have 3 distinct x-intercepts. Write your answer in a form where the exponents of b and c are both positive integers. So remember, an integer is a whole number, so a positive integer, positive whole number. We need to leave our answer where b and c have positive and whole powers. Right, so you might be wondering, where do we start? So again, this is an excellence question, as you might expect. So there's going to be quite a bit to do. So the key thing, these values here. So these are the x coordinates of the turning points. So we've got one at -3b to the power of 0.5 and one at positive 3b to the power of 0.5, which you might remember from part 2 of question C that we just did. So we know what x is at those points. So we can substitute those into the equation. And let's see what happens if we do that. So we've got y equals -1/3. We'll start off with the negative one. So -3b to the power of 0.5 cubed plus 9b. So again, anytime I see x in that equation, I'm replacing it with -3b to the power of 0.5 plus c. Let's try and simplify this a bit. So we'll start off by expanding the brackets. So the first thing to deal with on that first pair of brackets is the power, before we worry about timing it by -1/3. So we'll cube -3 and we'll cube b to the power of 0.5. So -3 cubed is -27. And then remember, when you have a power acting on a set of brackets, you multiply the power by the powers inside. So 0.5 times 3 is 1.5. And then we've got 9b times by negative 3b to the power of 0.5. So 9 times negative 3 is negative 27. b times b is b to the power of 1.5 plus c. We'll now times the negative 1/3 by negative 27b to the power of 1.5. So that will be positive 9 at the front, so 9b to the power of 1.5, and then take away 27b to the power of 1.5. You'll notice that I am only being careful to only do one step at a time. That's always the best thing to do, to just ensure that you don't miss anything, and that when you go back through and check your answers, it's quite easy to see what you were doing, and then it makes it easier to identify if you've made a mistake. Mistakes usually come from trying to do too many things in one go and not just working through the process. Maths is all about process. So just gradually working our way through that process. So we'll now simplify that. Now 9b to the power of 1.5 take away negative 27b to the power of 1.5 is negative 18b to the power of 1.5. So we can subtract those because they are like terms. They've got the same powers of b. And then plus c. So what we've got now is the y-coordinate of point P. We could have also used point Q. We'd have got a very similar answer. But this is fine as well. So now what we want to do is find an equation for the length of the red line. So the length of the red line will be the y-coordinate of P, which will take us from, on the graph, here to here, plus this extra bit from here to here. So this is going to be C. That's going to be the y-coordinate of here is C. So if we look at the expression here, C is your y-intercept, because that's your vertical shift up or down, just like it is in a linear or in a quadratic equation. That plus C is your y-intercept, because if we made x equals 0, that would be the only thing left. So we need to add C onto the length of this line. So the first thing to note is that the length of the red line, it has to be positive. So we're going to go positive 18b to the power of 1.5 plus C, because length has to be positive, length cannot be negative. And then we'll add C to that. So that gives us 18b to the power of 1.5 plus 2C. So that is the length of that red line. And again, if we use point Q, we'd have got exactly the same thing, because those lines are the same length as each other. Now, what we know is that for there to be 3 x-intercepts on this cubic, these red lines have to be longer than the purple line. So for 3 x-intercepts, the length of the red lines must be greater than the length of the purple line. So the reason for that, the purple line we can see goes up to the y-intercept, so our C value, and the red lines go from that C value to the turning points. So if those red lines are longer, then we can see that's going to make one be below the x-axis, therefore giving us 2 intercepts, and then so that's point P, and then it makes the other point, the highest one, Q, be above C, And of course, it's got to come back down again, so that gives us the third x-intercept. So the length of that purple line is c. So the length from here to here is c. So again, that's this c here. So the length of the red line, which we have established is 18b to the power of 1.5 plus 2c. That must be more than the length of the purple line, which is c. So if we just check back what the question was asking, find the condition that b and c must satisfy for the graph to have three distinct x-intercepts. Write your answer in a form where the exponents of b and c are both positive integers. So let's get the c's together. So we'll take away 2c from both sides. It'll just be negative c. Now we can divide by 18. Divide by 18. Now we were asked to give this with positive and integers, so we need whole answers. So I'm just going to rewrite the b to the power of 1.5. So 1.5 is 3 divided by 2. So we could write this as the square root of b cubed. That has to be more than negative c over 18. And now square both sides. So we get b cubed is more than negative c over 18 squared. So remember, squaring something means timesing it by itself. So we've got negative c over 18 times by negative c over 18. So when you multiply fractions, multiply the numerators and multiply the denominators. So negative t times negative c is positive c squared, and 18 times 18 is 324. And that is the answer. Okay, so as I mentioned before, that is an excellence question. There's no achieved grade given for this one. To get merit, you need to get an expression for the length of the red line. So that would be getting to here. And again, you would have got the same answer if you had used point Q, so that would be absolutely fine. You'd still get 18b to the power of 1.5 plus 2c. So remember, we made that positive because length must be positive. Length must be positive, so that's why it changed from negative 18b to the power of 1.5 to positive 18b to the power of 1.5. And again, we added c because that was the length of that part there, because this bit just gave us the y coordinate. So that got us to the x-axis, then we had to add the c on. And then for excellence, getting all the way down to here. They did actually accept if you got to here. In the exam marking, they actually accepted it if you left it at that stage. So either of those is okay. So that's question 1 complete.